says to use this information here to calculate delta y, actual change in y, and dy, which would be the change in y of the tangent line at that point. So let's try bring this up. And what this function looks like. 1/2 x to the third.
That wasn't the
Yeah, you
correct
didn't enter
equation.
that.
What?
You have a 3 in there.
Yes.
There we go.
All right. So at x equals 2, which, let's put a point there. There's this point right there. And they're saying between 2 and 0.1 away from 2, so 2.1, what's the change in y? And what's dy, which would be the change in y of the tangent line at that point. So we had this long discussion and talked about this at length, about how we find dy. So I'm just going to go back to that and remind you that dy is equal to, does anybody remember?
Prime of x minus dx.
That's exactly right. F prime of x times dx. Okay. And let me point something out here. This is really, it's technically incorrect notation, but it works well enough. If I divide both sides by dx, dy dx equals f prime of x, right? That's something that we've said before, that these are equal notations. This is Leibniz notation, and I think this is Newtonian notation. I should have known that. I should have really gone up earlier and researched that more. But I do know this is Leibniz notation. This is a different notation. So that's kind of a nice way to remember this here. dy dx, f prime of x, same thing. Multiply both sides by dx, you get dy equals f prime times dx. So if we want to find dy, which is really going to be close to delta y as long as dx is small, which it is pretty small, it's 0.1. So first we need f prime, not just f prime, but f prime of x, f prime of the x value that you're at, or at 2. So first let's find f prime, or y prime. What is it? Just 1.5? 1.5 x squared. 3 halves x squared. So what's y prime when you put 2 in it? 6. So f prime, or y prime of x, or of 2, is 6 times dx, which is 0.1. So 0.6. So that's dy, which is going to be close to delta y as long as we stay within a small dx of x. But how do we find delta y?
F of x plus delta x minus 2x.
Does that make sense? F of x plus delta x. Let's look at a picture of that. Okay. This is just the base. This is general function, not this function, but it's a general function. If I want to know the change in y between these 2 points, well, this is x, and this would be the other x value, which is it is delta x away from this other x. So this would be whatever x is plus that change in x. And this would be the point x, half of x. And this would be the point x plus delta x, comma f of x plus delta x. change, they change, find the change in y between this y value and this y value. I just need to take this y value, subtract this y value, and then I get the change, the difference between the two. So we need f of, what's x? 2, and what's delta x? It's 0.1, and what's x plus delta x? 2.1, f of 2.1 minus f of x, which is, we said, 2. F of 2.1, here is, well, call it y, but it's all the same story. 1/2 times 2.1 squared, or sorry, to the third, minus 1/2 times 2 to the third. Well, this is 4. And this is 4.6305. So when you take 4.6305 and then subtract 4, we're left with 4.6305. How close is dy to that? Alright. So how close is dy to this? Pretty close. Pretty darn. Pretty darn close. Within 0.0305. It's just off by that much. It's not a lot. 300ths of whatever. Meters. It's pretty close. Okay. Any questions about that? And that's really what differentials comes down to, or differential approximations comes down to that change in y. They both start at the same place. The tangent line of this function is at the same place. It touches the graph right there. So they have the same x and the same y value at that point. So what it comes down to is how much is y changing as you move away from x to the right or to the left. Does that make sense? That's all it comes down to. It all comes down to the comparison of y and dy. That makes the difference between the two values. It's like lethargic Tuesday. Lethargic Tuesday. You know what lethargic means? I thought you would. Oh, it's so insulting.
Oh,
Sorry, you don't like it when it's small?
can I run an errand?
What errand do you need to run?
It's a secret errand, Stuart. I can't tell anyone.
Well, get your pass out.
I don't even have it.
Save it.
Can I borrow someone else's?
You were having a rough morning. Until today is going to be hard.
I use a sophisticated agenda, not the petty ones this will provide.
Petty.
No, they're fine.
Oh,
I just quit using
I
it.
thought that was a funny adjective to use for an agenda.
Thank you.
Overrighteous agenda.
What's the date?
Support.
Thank you, everyone. I appreciate
Just
it.
looking out for
I
you.
wish I had a picture of
Just
this.
looking out.
This will help me through my difficult
I'm an
times.
adult.
Errand.
I'll bring the Dalton one day.
What?
Gosh.
Yeah, in 13 days I'm gonna hear it, right? Expect you're younger, so I mean.
Legally. Legally.
Let's not worry about when we can do certain things. Let's just worry about dy actually.
That is so weird.
Wow, they're fully.
Okay, we don't know what this function is. We can see a picture of it and a picture of the tangent line, and we know what point it goes through. And what they're asking us to do is find, to approximate f of 1.9 and f of 2.04 by using the tangent line. Okay. When it says use differentials, it means use values on the derivative, on the tangent line at that point. So this is 2, so of course 1.9, I think that's what they said, 1.9 would be somewhere right there. 2.4 would be pretty far away, it would be right there. It's going to be not a very good approximation, 1.9 would be a little better. 2.04, so that's not that far away. But farther than 1.9. increments are too small. So we're going to actually have to come up with the equation of this line and then be able to plug in x value into it.
Yes.
No.
Yeah.
We should open a window. I'm actually good.
Yeah, that's good.
So we need the equation of this line. So should be able to do that in algebra 2.
Rough.
Well, get to it. You see a point that it goes through here, and it goes through this point. 2 points on a line should be plenty enough to find the equation of the line. So do it. I'm not doing it. I'm not doing it. I'm doing it for you. Mhm. 1/2 x.
Negative.
Negative 1/2 x.
No. Yeah. Yes. Yes. Well, it's not positive. It's positive.
Right.
Negative.
Okay.
So it's negative 1/2. That's 2, right?
That's 2. Negative 1/2 because that's 2. It goes through 2, 1. Here's point 1. It goes through 2, 1. Point 2. It goes through 3, 0.
Yeah.
What do you need? You need the slope, right? You can find the slope.
-1.
Negative 1.
I was close.
What is this madness?
So y equals apparently negative 1x, and then we need the y-intercept. It's 3? Oh. I need to hear a good argument at least that the y-intercept would be 3. It's not that you know how to do it. You remember, you just think, gosh, what do I need? I need a b, right?
It crosses the
Plus b.
axis at 3?
Huh?
It crosses the axis at 3?
Okay.
So it's 3.
It's negative 1, so okay. That's at least a good enough argument that we could put 3 there. Okay. I'm going to remind you of this. Shouldn't have to, but here we go. You want to find the slope? Right? Then you need to know just the slope is how much does it go up versus how much does it go over. Rise over run. Right? How much does it go up? Well, it goes up from 0 to 1. Right? So what's the difference between that? 0 minus 1. That's the difference between these two. And I need the difference between these two. 3 minus 2. So negative 1 over 1. There's your slope of negative 1. You could just say, well, now I know the slope, but I don't know b. I want to know what b is. I want to solve for b. Do I know an x and a y? I certainly do. There's an x and y. There's also an x and y. This will be easy because it has a 0 in there. So 0 for y, negative 1 for the slope. X is 3 plus b. 0 equals negative 3 plus b, so b is 3. You could do point slope form. Y minus y1 equals m times x minus x1. Okay, so y minus 0 equals negative 1 for the slope times x minus 3. Y minus 0, that's just y, equals negative 1 times x, and negative 1 times negative 3. So, and when you know b, you can fill it in on this here. Right? There's one way, there's another way. Calculus class, you should be able to find it. The equation of a line given 2 points. Okay? So, there's the equation of the line that's tangent to that graph at that point. Right? And we want to find, or we want to estimate f of 1.9. That's going to be very close to t of 1.9. What would you say t stands for? Tangent, right? The value of the tangent line at 1.9. The value of the tangent line at 1.9 can be found by doing what? Huh? Nope. Not a song. I'm just a very lyrical person. Plug it in, right? 1.9 into the equation of the tangent line. So negative 1 times 1.9 plus 3. So 3 minus 1.9. 1.1. So this graph, this function, this curve is going to be close to 1.1 when x is 1.9. Then we want f of 2.04, which is going to be close to the value of the tangent line at 2.04, which can be found by plugging 2.04 into the function, negative 2.04 plus 3, which equals 0.96. There it is. Our approximation for f of 1.9 and our approximation for f of 2.04. Skip 23. We just need the equation of that line. So on. And it doesn't bother me at all that you guys don't know, you didn't understand like what it meant. You know, use the differential to approximate the value. It doesn't even bother me maybe that you didn't understand that you're supposed to find the equation of the line, but don't give up on yourselves and say, well, I don't remember how to find the equation of a line. You know what an equation of a line looks like. You know it's mx plus b. You should know point slope form as well. You should be able to at least say to yourself, you should be able to find the slope. Not because you remember y2 minus y1 and x2 minus x1, but because you know that it is the rise over the run. It's the difference between the two y values and the difference between the two x values. You should be able to reason all this stuff out. You should be able to invent linear algebra right now. You should be able to conjure it all back up and do everything you need to do with lines. Because it's that long ago. That far under our belts. Alright. Go on to 27. The measurement of the side of a square is found to be 12 inches. Okay? The square, 12 inches. Definitely you should have no idea what you're doing here. Or not no idea, but you should feel a little bit lost. We didn't talk about this, right? So don't feel bad. But follow with me. 12 inches with a possible error of 1/64th of an inch. So it's like your job to measure out these squares, little marks for, say, a machine to cut out a square that's that long, and you got your ruler, and you're really good, but also your eyes get tired, and so, you know, you might be off by 1/64th of an inch when you make your little mark. You know, if you're on the assembly line, you're making your mark, and you're within 1/64th of an inch. Okay, you might be 12 inches and 1/64th of an inch, or you might be 1/64th of an inch shy of 12 inches. Right? You're within that. They call it tolerance. Okay? So you say a tolerance of 1/64th of an inch. Use differentials to approximate the possible propagated error in computing the area of the square. So the funny thing about this is, here, let's make a graph. And I'll just go ahead and set the window so that it makes sense to us. We'll have squares that are 0 inches on a side up to 15, because we want to include 12. And then we'll go from areas of 0 up to, well, what would a square with a side of 15? What would its area be? If a square had a side of 15, what would the area be? So 225, so we should make y go to that value. Now we'll write a function that tells us the area of our given sided triangle, right? It'll say, oh, your triangle is 3 inches on its side. I'm going to tell you what the area would be. So what would that function be? What's that?
X squared.
X squared. X is the side of the square. You square that side to get the area, right? Because both sides are the same. Length times width is just length times length, side times side, because all the sides are the same. Look. So a square that has a side of, looks like 5, would have an area of, well, that would be 25. A square that has an area of, it's supposed to be 10, would have an area of 100. Right? That's what this function is telling us. A square with a side of 15 has an area of 225. What they're saying is, either it's us with a ruler, or it's a robot with a laser sight or whatever, you can get within 1/64th of an inch. Might be off a little bit here and there, more or less, by 1/64th of an inch. So we're dealing with squares, we make squares that have about an area of 144 square inches. Okay? But if we're off by a 64th of an inch, okay, so like 12 plus 1/64th, right? If we're off by 1/64th on the right side, our area is going to be a little bit bigger than we want it to be. We want it to be 144. If we're off by negative 1/64th, then our area is going to be a little less than what we want it to be. Okay? But what we're going to do is, so that there's this little a bit that we can be off by, 1/64th of an inch. We can be off by that much to the right or to the left of 12. What we're going to do is use a linear approximation to approximate the error that we might have. You see how that's a little funny? We've got this, we can be off by a little bit, so we can have this error in our area of the square, but we're going to have a little error calculating the error, right? Because our error using the linear approximation is not going to be exactly the same as the actual error. Okay. The error here, since we want to be at 144 square inches, is going to be like around 0.4. It's going to be off by the difference between 143.62524 and 144. If we're off on the other side, if we're off by a positive 1/64th, then our actual area is going to be 144.37524. We're off by 0.37524, whatever, however many decimal places you want to go to. We're going to use, we're not going to actually use the real function. We're going to use a line that's tangent to that function to calculate our propagated error. Propagated error will be, the error in measurement was up to a 1/64th. Propagated error is, now we're assuming it's 12 inches, but we might be off by a 64th of an inch. So the error on top of that is, our area is going to be off also. And then if we calculated something based on the area, then that's going to be even more off. When we calculated something based off of that thing, then that's going to be even more propagated, right? You know what propagated means? One thing begets another thing. This causes this to happen. Propagation. So, you saw the function. This is the actual function. That is the area function of a square. square with a given side length. We know that we just said the area function is x squared. And x is 12. A prime would be 2x. And delta x, the little bit we go to the left or the right of x, is what? 1/64th. Okay. And again, what we want to know is delta y. What is the real change between the area we want, which is 144, and the area we might get if we're off? If we're off by positive 1/64th, we could get up to this much area, 144.37524, and so on. Okay. Well, we're not actually going to find the actual error. We're going to approximate the area with the linear approximation. This is really close to dy, which is the change in y of the tangent line. And that is, as before, f prime of x times dx. Or in our case, a prime of 2, no, not 2, of what? 12, not 2, 12, times dx, which is 1/64th. And actually dx, it could be positive 1/64th or negative 1/64th. You could be off by too much or off by too little. Let's see. I'm not sure. But I do know that a prime is 2 times x, and I know x is 12. We're going to multiply that by 1/64th. So we did 24 times 1/64th. 0.375. How close was that? Really, really close. 0.37524 is the actual value that you're off on the area. Well, we want to do the other one. What's the other one? Right. Times negative 1/64th. So it's 24 times negative 1/64th. What? Negative 0.375. So, forget how they want this answer, or maybe standard.
Oh, it says plus or minus 3.
Okay. 0.375 is the same. So yeah, I would say the propagated error would be 144 plus or minus 0.375 inches squared. Or if you were to just write that, that would be fine. That's the actual error, right? How much you're off by.
Okay, so you're off
Yep.
usually.
Yeah, I just haven't figured out exactly what my scheme is.
50 points a can, unlimited cans.
And those points will be uniform.
Ah.
Do we get something?
And how many unicorn points go into a unicorn?
Well, 100
What's the conversion?
million
No.
unicorn points is worth 1 shroom buck.
Oh,
10,000 shroom bucks is worth 1 participation point.
right.
10,000.
So there's your conversion.
Perfect. And how many real dollars are in a math box?
Well, math bucks are in imaginary numbers, so
Oh. You know what would be really smart is if you had like $10 into a math buck and then 10 math bucks into $1. You make money crazy.
you confuse me. I'm confused now.
See, everybody gets
I am
$10
so
and they
confused.
get 1 math buck, but then they get 10 math bucks and they traded in for $1 more. So they lost $99. And you gained $99.
Wow.
Some people are
All right, the
so
measurement of the edge of a cube is found to be 12 inches. All right, all sides then of a cube would be the same. With a possible area of error of 0.03 inches. So we can find the side of the cube. And again, imagine that there's this, maybe it's a box making machine. The box making machine measures its folds, 12 inches, and wants this side to be 12 inches, and it folds the box up so that it has 12 inches on each side. But it could be off by either plus or minus 0.03 inches. Okay, and if what we want this box to do is hold a certain amount of packing material or Furbies or Mogwais or something, then we may have too much room or too little room, depending on how much we want the box to hold. So, how much could we be off? That's what we're going to find out. Use differentials to approximate the maximum possible propagated error in computing the volume and the surface area. Of course, the surface area would create a problem if you're making boxes and you want to know how much material to order. If you're always off by 0.03 inches too much, then you'll be short your materials, right? You won't have ordered enough. So you want to know how much the error is, you want to order more than enough for the propagated error. Okay. So for part A, which would be the propagated error of the volume of the box, first we have to have a volume function. It's a function of the measure of the side. What's that function look like? S cubed. The derivative of the volume function, 3s squared. We want to know how much is the error, or I guess we want to know delta V, which is close to dV, which is equal to, say, V prime of S times ds. Does that make sense? Okay. We changed y and x around. We're using different letters, but it's all the same thing. Okay. So for us in the area, we have 3 times. What's the measure of our side length? 12. We hope, but we could be off by 0.03, by plus or minus 0.03, right? By, can I just do this?
Yep.
Right? If I did 2 equations, one with plus and one with minus, wouldn't it be exactly what we're saying here? Right? Just multiply it by a positive and a negative, all that's going to change is the sign of the answer. So our possible area or error in the volume is plus or minus 132.
Yes, you didn't get that wrong.
I don't know, that sounds big.
I got
432
12.96.
times 0.03.
Oh,
Oh.
you were giving me the pieces. Okay, thank you. Usually that is what I ask.
No, I added 0.03.
Oh, you added.
Yeah.
Well, here's an answer for you. 12.96.
Inches
Yeah.
cubed.
Inches cubed. That seems kind of big. 12, almost 13 whole cubic inches that you could be off by.
Well,
Which means if you go the wrong way and you're trying to hold like this perfect amount of stuff, marbles or something that you pack in really tightly, if you're off by a negative 0.03, you're not going to have enough room in the box to hold the stuff you're supposed to hold. So that could be a big problem. So you want to make sure that you're working with your tolerances and you're telling the company that's packing marbles into your boxes, you can hold this much, and they might have some extra room. I'm going to give them the low number, right? Does that make sense?
Yeah.
Giving that low number, and they might just have some extra room in those boxes. Now, let's part B. Find the propagated error in the surface area. Okay, that function is,
V squared.
what's that?
S squared.
S squared.
And V squared.
Well, S squared would give us
Ah, so
this
it would be
side
S squared times 6.
times 6. 6S squared There's six
Just
sides.
How many sides are there?
This gives you the area of one side. This gives you the area of all six.
Then you
And
want
then we
the
need a prime,
derivative.
Yes.
which is
That's right.
Well,
Yep, square root.
12s.
you want to multiply that by there.
Then there's five.
Right, we want to know what's the possible change in area that is close to dA, which is equal to a prime of s times ds. So a prime of our s would be 12 times 12 times our possible area, which is plus or minus 0.03. So 144 times plus or minus 0.03
Oh my goodness, I found it.
is what? How much?
4.32,
4.32,
which is squared.
which is squared.
I have a question.
Yeah?
Does any three-dimensional figure have four sides?
It says six sides.
No, not this one.
Oh, is there one that exists that has four sides?
Pyramid, but you said a
I
square
just,
pyramid,
no,
and
I
that would
did.
have
I said a
five.
triangular pyramid.
No, you
Triangular
didn't.
Yes, I
pyramid.
You were
did.
thinking about a square one. You said square. Has
No,
four
you
sides.
said square.
I did not. I said a square does not
I
have
said a
four
pyramid.
sides. How many sides is a square pyramid?
I didn't say
Five.
square.
Thank you.
What?
No, I didn't say
Oh, I was
square.
just gonna say, do you think that's gonna break
Three words
the pen
from mouth
eventually?
It's made because I did
Oh,
replace
that's
these.
cool.
Yeah.
Can you write with just that?
No. You have to replace
This
those?
pushes the mechanism into the pen. Yeah, look at this thing.
Maybe you need a new pen. What?
It's all worn down.
Oh, look at that. Oh,
Do
It's
that.
your dog.
But there's asbestos.
Do math so hard. Yes?
One time in Miss Reed's, they took the little pointy thingies off her pens and they hid them all over her room.
That's funny.
Who did that?
Remember that?
I don't know.
That's terrible.
That's so funny.
Alright,
Give it to me.
so, hey, you're hiding your knowledge all around the room and you're not trying to find it. Our error is plus or minus 4.32 inches squared for the area, surface area. So the guy who's in charge of ordering all that flat cardboard to make the boxes needs to keep this in mind, that you may need to add 4.32 inches squared to every box that you want to, you order material to make. You want to make sure you have enough. Okay? Because that machine might, its saw blade might wobble by 1/64th of an inch or something. Make your boxes all off. I watched How Things Work. 43.
Used to be my favorite show.
Know how stuff works.
Oh, I used to watch that.
How it's made, I don't know. It's like old.
Yeah, it was my
No
favorite
way.
show.
It's way ahead of its time.
What's next? 33?
43.
43?
It was so, the guy was so calming.
Yeah, he was like,
It was nice.
that one, have you ever seen him make hot dogs? Watch the class.
How it's made is so, it's like, you know, how do they make snowmobiles? Well, first they make the snow
No, those
part,
were
and then
the
they make
cool
the
ones.
mobile part, and they put it
Those were
together.
the dumb
Next,
No.
this doesn't go into very much detail.
The cool ones were like the baseball,
Or light bulbs.
hot dogs,
Light bulbs is cool.
or light
Hot
bulbs,
dogs
or
disgusting.
paintball. Yeah.
Like
No,
you put your hand in hot dog this.
All right,
or
Okay.
wooden clocks. That one was cool.
all right. So what we need to do is imagine that there's some function out there that this there's an x value in here that's just a little bit off of an x value in the other function. It's actually very easy to calculate. Okay, so let's break that all down. So what function is it here that we're working with? No, that's a number. What's the function? Oh, the square root function, right? And what square root is this close to that's easy to take the square root of? 100. Yeah, so it's very close to the square root of 100. We're a little bit off. How much are we off by? 0.6. We're off by 0.6. So it sounds like our x is what? Like where's the x that we would like to be at? Is 100. And we are off by delta x 0.6. Okay. F of x is apparently what function again? Square root of x meet f prime. That is?
1/2 x to the negative 1/5.
You got it. Or we could say 1 over 2 root x. Okay. When we want the actual y value, we don't want the change in y. We can actually calculate the y value. So the f of x will be very close. Well, f of not x, but of x plus delta x. Okay, it's going to be very close to. Well, we'll start at f of x, and then we'll add on that change in y. Okay, because this is a y value, right? And if we add delta y, actually these would be exactly the same, right?
Yeah.
Does that make sense? Delta y, the change in y between x and x plus delta x. Right? I go up this, so I go from x and I go to delta x, and that means on the y value go from here to there. And if I add on that little bit to this y value, I'll have the next y value. Okay? Well, delta y is very close to what? That's dx. Delta y, we've been doing delta y. dy, right? And we calculate dy by doing what? F prime dx. This is also dx. This is dy, which is very close to delta y. Actually changing y. So we'll take our original f of x, okay, x being 100, so what is f of 100? 10 plus f prime of x, so here's f prime, 1 over 2 times the square root of 100. What? What did you say? Times 0.6. You say 1 over 20? Yeah, that's 1 over 20. So 10 plus 0.6 over 20. Whatever, you can just plug it on in and see what we get.
9.97.
9.97. That's our approximation for the square. Oh, you know what we did? What did we do wrong?
You're at 10.0.
So did I.
Oh, I added.
Plus or minus.
Oh, yeah.
It shouldn't be plus or minus, right? It should be minus. Right?
What did you
I stand by 9.97.
Why is it minus?
Because of
Yeah, we're
the-
under 100. We went from 100 back
Oh,
to
sorry.
99.4.
Well, why'd you write plus up there?
Because I'm an idiot.
Good thing it's not profitable.
You confused us all.
It's Tuesday.
Wait till Friday. I'm going to have all this stuff done.
Humble Tuesday.
All right. 10 minus 0.6 over 20 would be
Be so mean about it.
Isn't Mike still there?
9.97. Should be right, yeah. It was the reason why people were getting 10 point something is because I said plus. Right?
Yeah.
It should be minus.
You're very
You guys
9.97.
said something. Way to go, Mike.
Alright.
You all feel just stupid.
Way to get it right again. Sure.
I went
That's
for
basically
one
what
time,
you're
might
saying
just
to
be
Mike.
wrong.
You're so right.
Man.
Right in his face.
All right. That's our approximation for the square root of 99.4. How about if we see how close we are? What is the square root of 99.4?
No, I like it.
What?
9.97.
9.969. 9.97 if we round to the nearest hundred.
That's a good one.
Chance.
Oh, yeah?
This is cool stuff if you don't have a calculator. If you have a calculator.
I know, right?
Do you love it?
Well, if you didn't have a calculator, it's still.
Right, that's what I'm saying.
Oh, if you didn't have it. If you don't, yes. Yeah, this is really left over from the times where we didn't have calculators that could do all this
So
stuff.
this book kind of behind.
Yeah, let's throw it away.
Oh my gosh.
Space for this stuff. And the whole book will say use a calculator too.
I really don't
Press
want
these
to.
buttons. All right, what is the function we're using this time? The third root of x.
I just put 3 as my answer.
What x value is? Are we like? Would be an easy x value? 24. 27.
27.
27. Okay, here.
27.
Stop talking. Y Why is 27 a good choice?
Why can't we
3
choose
times
one?
3 times
Let's
3.
do one.
27.
There you go.
Why does it work?
Right? 25 sounds good because 5 squared is 25, but we don't want squared, we want cubed. Right? Okay. So what's delta x? Yes. -1.
So it's left with
We're short of 27. We're below 27. We are a delta x of -1 from 27.
We need to know f prime.
Of course. We're in calculus. So we have 1/3 x to the -2/3, or 1 over 3 times x to the 2/3. And again, f of x plus delta x can be approximated with f of x plus f prime of x times dx. That's that original y value plus our approximation of a change in y. So f of 27 minus or plus a negative 1 is equal to f of x. What's f of x? Since x is 27. 3 plus f prime of x. So here's f prime. 1 over 3 times -1 to the 2/3. Times dx. No, that's what I did wrong. X is f prime. F prime. F prime is 1 over 3 times x to the 2/3, but x is, what is x? Yeah, I put in delta x. 1 over 3 times 27 to the 2/3 times dx, which is -1. So this just means we're going to subtract it. So 3 minus, because I have this -1 here, 1 over 3 times, how do we take 27 to the 2/3? That's wrong. What's this part? Cubed root. What's the cubed root of 27? Squared 9. 1 over 3 times 9. So 3 minus 1 over 27.
Yep.
So 3 minus 1 over 27. All right, now let's go to the calculator. Do decimal.
2.96296. And I can math bracket. It's 80 over 27.
Yeah.
Math bracket. Which I like to do.
Because this would be 81 over 27.
Yeah.
81 minus 1. 80 over 27. And what is the actual cubed root of 26? It's like this. And that's what we would hope.
How do you do cube root?
Something to the
Is it 1/3 power? What? No? Put it backwards or something like that? Something like I would do.
You already told me this. Because you already told me.
My calculator, I didn't use it for a lot of the reader. My battery was yeah. It just still works.
It did.
No, they're like still in there. Battery acid. Other than that, though, it was good. Where did you see it? It's in my dad.
Oh yeah. Sorry.
How was your Saturday?
Do it.
which means be quiet until I ask you to stop being quiet. Stop being quiet.
Stuart,
Keep it up.
it's not done. Calculator just
Wow.
this deserves like a ceremony or something.
It's weird.
Oh, this has it's had its time.
I've had the same calculator since I was in high school. I don't see why that would be breaking.
Not all of us are as lucky as you.
They're like the most resilient things in the world.
They're all basically bricks of math.
Dropped it, driven over it.
You've
put it
driven
on
over your
space shuttle
calculator.
and it took off. It's so good.
Just so Stuart, you would never. We'd probably cry if you ran over your calculator.
I would cry.
It would
I
still
want
be
Quiet.
disease if he
Number 53. 53. Page. Please discuss 53 with us.
Alright, well, when, so I'm just showing you. Okay, the change in accuracy, it becomes closer to the value of delta y as delta x decreases.
Very excellent. Yes. dy becomes closer to delta y. Right? So if we were to look at a function and its tangent line at a certain point, remember this is all about the tangent line's approximation of the blue curve. How close will the black line be to the value of the blue curve? Well, it'll be closer the smaller delta x is. Here's x. And just so that we can see it, we'll make it big. Here's delta x from here to there. If delta x is big, then how would you compare dy and delta y? How do they compare?
well,
As far as the accuracy of dy to approximate delta y.
let's see.
Not very accurate, quite inaccurate. What effect does making delta x smaller have? More accurate. Closer delta x gets to 0, the more accurate dy is in approximating delta x. Wow. Or delta y. dy and delta y. Yes! That's the only one we didn't do, I think.
We didn't do 90 either.
Yeah, I don't think we did 11 or 19.
Okay. The short story is differentials are easy, super easy to find. By the way, yeah, seriously, dy is what we call the differential of y. Dx is what we call the differential of x. Just some vocab. Okay, dx is a differential of x. So one way to think of that, the meaning of that is the really tiny change in y, the really tiny change in x. So how are we going to find the very, very tiny change in y? Well, it's always the same. F prime of x times dx. So dy equals
It's like,
6x.
there's like an optimus sign.
so what's f prime? Y prime? 6x. 6x dx. There's nothing for dx, but it's just called dx.
That's all we have to do.
Oh yeah. Boom, done. Circle it, call it a day.
So dy is always just the derivative times dx. Derivative times dx.
6
If you use the chain rule to find the derivative, then you will do that and multiply by dx. If you use the quotient rule to find the derivative, you'll do that and multiply that by dx.